Did you get your budget stuff figured out? Not really, because I'm waiting on
Okay, people are quieting down. Is someone coming in? There's someone coming. Okay, I'm really glad that Kendall agreed to give a talk in this series. She's down the hall from me, so it's hard for her to say no. Walk by her office multiple times a day, but she's been here for a year and a half at UW, joined the faculty in oceanography. It's been great to have her here, and she works on really relevant topics in summer series. So,
Oh, I'm just gonna hide them. It came back again? I've hidden them, it's the other one, I've hidden them twice. All right.
okay, so take it away.
All right. Well, hello, everyone. My name's Kendall, as you know, and I am a coastal ecogeomorphologist, which means I study how coastlines change and the interactions between biology, geology, and physics. So basically, I'm just afraid of chemistry. And today I'm going to be talking about kind of my favorite place in the world, which is this picture here, which is coastal Louisiana. And what I'm going to be talking to you about is climate change adaptation that needs to be happening now. I know a lot of the things that you've been talking about this quarter have focused on marine carbon dioxide removal and those type of engineered strategies, which are great strategies going into the future that will really help people who have the time to wait. But there's a lot of communities, especially communities of color, disadvantaged communities, uneducated communities who do not have this time to wait, and we have to act now. And so this is where most of my work has been focused on working with communities who need to do something right now. What can we do to mitigate these changes and plan for the future? So this is just from one of my favorite field days. I just wanted to start with it because I'm not from Louisiana. I'm from Minnesota. When I moved down there, I never planned on moving to the South. I thought I was doing a crazy thing and I fell in love with the place. And so I want to give you a little taste of that to understand why I'm so motivated by the science as well. So I was out collecting sediment cores and measuring waves. There was no waves on this beautiful day. You can see this is the horizon line here, and then just beautiful clouds. And then you can see these little things out here. Those are oil rigs out in the Gulf of Mexico. And so if you look out on the whole coastline, you'll see these oil rigs kind of scattered along the coastline, kind of breaking off that beautiful view. Shortly after this picture was taken, my boat died and I had to fix the motor while the sun set. So this was a particularly nice moment in a kind of crazy day. But kind of this area of coastal Louisiana, you see these little bits of land. The whole southern part of the state is very low-lying marshlands that are critically important for the United States and the world ecology. We're going to go into the reasons why they're important. But a lot of the land here is just this very low-lying, right at sea level land. So why do we care? So if we look at population around the world, we're going to get it to go eventually. There we go. This is a map of global population, and like the bigger bars mean more people. And what do you notice about this diagram? What can you see?
Coastline.
You can see the coastlines, right? There's an outline of nearly all the continents. Australia kind of disappears here, but you can see that most people live along the coasts, right? And so understanding these coastal dynamics and sea level rise are extremely important because it's going to impact most of the people that live on this planet. And on top of that, basically all the hazards that go along with the coast are enhanced with climate change. And so all of these people are subject to much more change and they have to kind of come up with a way to adapt. And I'm going to quickly change this again. My computer is having a fun day right now. All right. So what I'm going to take you to is, if you're not familiar with coastal Louisiana or the United States, so here's a map of the United States. Here we are sitting in this room today. We're going to take a nice 5-hour plane ride and then a 45-minute boat ride down to the bayous here. All right. And so what's special about coastal Louisiana is that the Mississippi River drains most of the country, 2/3 of the country, right? And all of that sediment and nutrients are all funneled into kind of like America's toilet is what is often termed. There's a lot of nutrients coming out, resulting in a large dead zone, oxygen minimum zone here. Also, all of that sediment basically built almost the entire state of Louisiana. So all that sediment coming from the entire country is building new land. And so that is really kind of what that land is made up of. What does it look like? So these are the marshlands of those coastal areas where people live and work. So it's very low lying, filled with creeks and ponds, and it stretches for miles. And so this kind of ecosystem is incredibly important. We host a wide range of animals. Bird people really love the wetlands, but also filters out nutrients. So all those nutrients coming down the Mississippi River get filtered before they enter the open ocean. So we have reduction in nutrient loading. They also trap sediment to help build land. And they're also really culturally important. These are the salt marshes. If you just go inland a little bit, you'll get into the bald cypress. These are freshwater marshes, which are vital ecosystems that also support a whole nother diversity of animals that only live in these type of regions. Additionally, these trees have a lot of cultural value and are viewed as ancestors in some of the communities there. And people live along this water. So this is where one of my field sites, like a little floating church on one of the bayous. So you just drive past that. There's one little road next to a little bayou, a little river. And so you can see people are right on that water. And so what happens if you have sea level rise here? Do they have time to wait? Not at all. These are the houses I would stay at for my field work. They're elevated 2 stories above the ground in order to basically at regular high tides, and tidal range there is only about 30 centimeters. At high tides, there's water underneath these houses. During storms, the water still might get into here, given the high range of storm surge. All right. People are still buying new houses down here. Actually, there was a for sale sign just down the street from here. So people are still buying houses. People are still living here, even though you're at extreme risk. And there's actually a lot of engineering that went into these of how high is it before you hit too high of winds from hurricanes. So basically we're trying to find the sweet spot between winds from hurricanes and flooding from the storm surge, all right? And there's a whole other, there's a whole nother talk I could give about, well, whose property is it if the ocean is underneath your house? Right, so thinking these are questions that the people that I work with think about every single day. Most of them those elevated houses are next to the bayous where you have your fishing and shrimping boats, right? And so that's a main economic driver of the area. And so being able to shrimp and needing the right salinity conditions to be able to do this in an effective way is how these people live. The literacy rate in the state of Louisiana is 50%. And so most of the people who live south of New Orleans cannot read above a 3rd grade level, right? However, when you talk to them, they all can tell you about the sea level rise problems. All right. This is kind of some of the cultural value of these. So along the Mississippi River, right around Christmas time, we all build bonfires. And this is to help Papa Noel, the Cajun Santa, get to your house on the bayou. So intimately connected with the coast. Here is the Zydeco bands will go out on their boats. This is modern day. Here's an accordion and they'll be singing on the water. And this is just part of everyday life. And so everyday life is changing along this coast. So these are what the communities look like. So this is when I talk about the bayou. This is kind of what it looks like, or the Mississippi River. And then we have those houses right upon that. And this is the landscape that we're going to be investigating here and of why we need to make coastal changes now, because all of this land is at or below sea level practically. There's an engineered levee that lifts it slightly above. So I say we have this problem. How big is the problem? So the state of Louisiana has lost the area of land the size of the state of Delaware since 1930. If you do the math out, this comes out to a football field of area lost every hour since 1930. So this is not a small problem. To look at the land change since 1930, the red areas are land loss. and the green areas are land gain. And so you can see, while there have been some small gains that I will talk about, we're having widespread loss of nearly all of these coastal wetlands. To give you a context of where we are, New Orleans, the port city, is right here, and this is the Mississippi River. All right. So why do we care about this? Part of it is that, you know, there's all of this important things I've talked about the people and about the animals, but also infrastructure and ports. Basically, the big shipping containers that deliver stuff to the entire United States come up this river and come to the port of New Orleans. Because of changing water levels, we have to dredge this river more often, and it's harder and harder for boats to get in. So there's also an infrastructure problem. And this infrastructure problem also, this is from one of my field sites as well. Anybody know what these are? These are graves. So the cemeteries that were built on high land, they're built, you know, at the highest land you can find, which is 20 centimeters above sea level. And these cemeteries and all the cultural history are washing into the water, along with the global, the infrastructure for the United States industry. Okay. We don't have time to kind of think about these. Now, what's causing all this land loss? There's a whole myriad of problems, but basically, to give you an idea, so here's the state of Louisiana again. Here's that bird's foot delta, or that part that was sticking out. And the colors here represent the total subsidence rate, or total subsidence rate. So when we talk about sea level rise here, we often use the like 3 millimeters a year of sea level rise, right? Here, this total subsidence rate is basically combining that sea level rise rate with other land sinking properties that I'm going to talk about in a second to get kind of a relative sea level rise rate, or like what it actually feels like the ocean is doing. So here in Washington, we talk about 2 to 3 millimeters per year. The Atlantic Bight, they're saying, oh my gosh, we have 5 millimeters per year sea level rise, relative sea level rise. Here we're getting up to 20 millimeters of sea level rise a year. So that's 2 centimeters of sea level rise every year that's happening in this area. And it's very spatially variable, but practically the entire state is above the eustatic level that we talk about for most of the country. So everything basically of this light green or higher is what we would consider kind of extreme rates of sea level rise. And so this relative sea level rise rate is what is causing this wide scale loss. What is causing it? Well, so one of them is levees. So I showed you that Mississippi River comes down here, right? Following extreme flooding, there was levees built on the side of the river. Basically, they piled dirt on each side to keep the river put. However, rivers are supposed to kind of flood over their banks and deliver sediment to the adjacent areas. When we added these levees, that was no longer able to happen. So these marshes here that needed that mud to survive were not able to do so, and that caused accelerated sinking. I've already covered eustatic sea level rise. Then there's also kind of the downward movement of the land. So these other ones are kind of the lack of upward. But here's the downward movement. So one thing is that this is a delta. So there's tons of mud coming down the Mississippi River. When it deposits there, it's heavy. And so you could think about a kitchen sponge and you start like adding piles of stuff to it. It starts to depress, right? Make sense to you guys? Well, basically that's what the Mississippi River Delta is doing to the continental crust. Okay, and all the sediment that's underneath it is that it is so heavy that it starts to push down. So there's this downward movement of the sediment. Additionally, we've helped out that downward movement by fluid withdrawal. So actually withdrawing drinking water and oil and gas, that actually kind of leaves voids in the underground, and then you have the ground that sinks down to fill those voids. So extreme withdrawal of water and oil and gas has led to this increased rate. We can actually see that peak with the peak extraction rates in the area. So we know that that is actually a pretty substantial change. And then lastly, another huge driver of land loss is none of this area is protected. And so oil and gas companies can dig canals through the wetlands to be able to drill for oil. And while you think like digging one canal will not affect the state, I'm going to show you a picture of what this looks like. So all of those straight lines that you see, those are all canals that were dug by oil and gas companies, and then they kind of end in a little cul-de-sac area, and that's where they build an oil derrick. And then once they're done, they just leave it there. Any of the marsh that remains becomes impounded and drowns eventually. So this is a pretty substantial issue, right? My undergraduate advisor always used to say, that like, if you see straight lines, it means God didn't make it. So that's what I always think of when I see this, is that, you know, there's so many straight lines. This is so anthropogenic. And so this is what we're talking about with this coastline. Why do we care? So the salt marshes, I've already said, so we have these extensive salt marshes. Why should we even care that it's disappearing? They look pretty low lying. How many people could possibly live there? You know, is this worth a whole career's worth of research? I would say yes. So there's the habitat for the little salt marsh sparrow and fish nursery habitat. There's great recreation value. Louisiana is sportsman's paradise, so there's great economic value in the fisheries there, like just for fun as well as large scale fisheries. There's cultural values, so a lot of the indigenous peoples in the area really rely on the coast as part of their cultural history. So for example, you know, that low-lying ground, the origin story for the Homa tribe is that crawfish went down and dug up the earth and made the marshes. And so they rely on this sediment transport, of the transport from the channel outwards. That same actual physical process is part of their origin story. We have the water filtration, the carbon storage. So marshes actually can store a lot of carbon to reduce climate change. I'm not going to talk much about that today. And they also are a buffer for storms. So basically that marsh, if it sits in front of your house, when waves come at you, the marsh will dissipate some of that energy, make the waves have less power, and you'll have less erosion. And so this is what these marshes are. Before I get into like my research, what I wanted to just kind of show you is what an actual marsh looks like, because the ones out here are teeny tiny. How many of you guys have been out in a marsh? Yes, okay, this is so exciting. I feel like normally when I talk to Washington, people will be like, I don't know. But basically, this goes on for miles, but basically the water here, it's probably about 1 meter depth, and then there's a quick step up here to this vegetated marsh platform. All right. And so this is one of my field sites. You also can see there's kind of like a change in vegetation. Can you see that difference? That actually the different plants grow at slightly different elevations. So back here, there's like it's a centimeter higher. And so the plants grow, 2 different species of plants grow because of that range in elevation. Now just put that in context of sea level rise, where you're having rates of 1 to 2 centimeters of year change. So think about how those plants have to try to adjust. It's not going well for them, I gotta tell you. So how do marshes work? I'm gonna give you a big primer, a little bit of a primer on how marshes work. So you have your marsh grass and then that platform where you step off into the water, right? And so how marshes work vertically is that there's the tides go up and down. As the water comes up, it brings mud and that deposits, making that marsh grow taller. At the same time, that flooding actually makes these plants happier, a certain middle ground of flooding. And the plants make more organic sediment, allowing the marsh to grow taller. So in theory, if you have more flooding, so sea level rise, this marsh should be able to grow faster and you'd be able to keep pace with sea level rise. And so there's these feedbacks between the sediment, the flooding, the physics, and the biology of the plants that should be able to maintain this elevation. What we find now, though, is that sea level is rising too fast for the marshes to be able to keep up. But so you have this really ecogeomorphic system. In the lateral component, basically you have your marsh and the waves come and impact here, and you can imagine that those waves hit the edge and cause erosion, right? So you have land loss happening here, but the plant roots themselves help hold the sediment together and prevent erosion. So you can see from the vertical and the lateral, we're kind of depending on all of our branches of science. And so this is how marshes work. And this is the basic underpinning of how we can think about how to preserve these landscapes and how to protect and build new ones to be able to withstand sea level rise. Everyone with me? All right, because now I'm going to tell you a story about my research and how I kind of found my place in helping develop plans for coastal Louisiana. So I'm going to tell you a story of these 2 marshes. This one over here erodes at about 0.5 meter a year. This one at about 1.5 meters a year. You might say, well, that sounds really interesting. Very cool, Kendall, but you just told me that, you know, different wave conditions and stuff would cause different erosion rates. But what if I told you these 2 marshes are actually only 1 kilometer apart from each other? And they're actually the same plant species that are occurring here. So this are 2 marshes within Bay Jimmy, within Barataria Bay, Louisiana. So we're way down here in the south. And there's this northern site and southern site. And this northern site is eroding half as fast as that southern site. All right. And so I started to wonder why. And actually how I got tipped off to this is I was doing community outreach and some fishermen told me that this was happening. And I said, oh, really? That's weird. I'm going to go check it out. And so I went out in a boat This was actually the most oiled area from the Deepwater Horizon's oil spill. So this area has been really well studied recently because there's still crude oil sitting on the marsh. Well, my first suggestion here would be, well, maybe this is just maybe they've just noticed it recently. Maybe this isn't a real deal. Maybe, you know, maybe this is just some fisherman noticing that his favorite fishing spot isn't working as well anymore. So I went and looked at old imagery. And so I looked at Landsat imagery between 1877 and 2017. So dark blue is land, light blue is water, and the yellow is land lost between 1877 and 2017. And you can see between that northern and southern site, we still do see that that northern site over that longer time frame is eroding about half as fast as the southern site. So this seems to be a real phenomenon, but maybe just maybe there's a nutria family. They're like little otters that like to eat marsh grass, moved into this island and they've lived there for generations and they're eating the marsh away. Right? But if you start to look closer, you might notice, well, actually, there's this asymmetry between the north and south here and here. And now I'm going to take and zoom out to the whole of Barataria Bay. So this black area is where I showed you. And you'll start noticing that this asymmetry is everywhere. Here, 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 here. But one too far, all right? And so what's interesting about this is that this is clearly indicating a process that is driving marsh loss in an asymmetric fashion. So there's something that we can understand here to hopefully help us understand how to prevent this loss. And this is where I started really getting my thinking cap on. So I went to think about these two marshes. And I said, okay, well, if I were, you know, someone who studied physics, how would I view this? And I said, well, maybe there's just more wave energy impacting the southern side. They have the same fetch, so basically the same area for wind to blow over to build waves. But if there's just more wind coming from the north, this south side we'd expect to erode, right? Make sense? So I went and looked at 30 years of wind data. And I calculated the wave power associated with that wind speed. So basically, if you have bigger winds, you have more wave power or energy in those waves, right? So it's a nonlinear interaction. But basically, I calculated that using 30 years of wind data. I didn't trust the data that I didn't collect, so I went out and put a sensor out there and measured it for a year as well and calculated the wave power. And basically, no matter what you do, when you calculate this, there's actually more wave energy coming from the south impacting the northern shore than the other way around. So in other words, we would expect the northern shore to be eroding faster. So physics doesn't win here so far. All right, so I gotta keep thinking about what's going on here. And I start thinking, well, what's weird about Louisiana? That's kind of an endless question, but the answer here would be thinking about those water levels. So in Louisiana, the tides, I told you, are already pretty small, like 30 centimeters maximum, but there are more water variations due to the wind direction. And what I mean by this is when I go out to drive the boat, I wouldn't actually look at the tide charts. I'd look at the winds because I know that if the winds are blowing from the north, I would get stuck. And so I started to think about the mechanism that would happen. So basically the idea would be that when the wind blows from the south, it's going to pump water from the Gulf of Mexico into Barataria Bay, increasing water levels everywhere. However, when the wind blew from the north, it's going to pump the water out of the bay into the Gulf and lower water levels everywhere, right? So maybe this has something to do with what's going on, that we see this asymmetry, and we see an asymmetry in the water levels. Well, do we see this in real life? So I went out and looked at 30 years of data from Grand Isle. So here on the x-axis, you can see wind direction. So wind from the south is in the middle, and the winds from the north are on the edges. And the different colors represent different wind speeds. And basically what you see is when the winds blow from the south, the water level is higher, and that's exacerbated when the wind speed is higher. Didn't trust data I didn't collect, so I went out and collected my own data again. And you see the same pattern. It just doesn't have 30 years of data, so it doesn't look quite as nice. All right, so but we are seeing this asymmetry between, you know, the northerly and southerly winds causing higher or lower water levels. And so from this, I developed a hypothesis that basically when the winds blow from the south, impacting that north shore that didn't erode as much, the water level's high, the waves are going to hit the plants or the roots, which can dissipate energy, and you don't have erosion happening. On the other hand, when the winds blow from the north, it's going to drop the water level, the waves are going to impact beneath the plant roots, so there's no cohesion happening and you get high erosion. And so I went out to test this. And kind of just to show you what I mean about the strength of the soil. So this is from a previous paper by Gene Turner, but basically this is soil strength with depth. And you can see in the surface, the soil is stronger where there are plant roots and it decreases. Eventually, if you go really deep down, it gets stronger due to compaction, but you'd be swimming in Louisiana by the time you got to a meter depth. So I went out and measured, do we see this change in strength? So this is that soil strength with depth again, and I saw that same pattern. So those roots are strengthening the soil, so maybe my hypothesis could be correct. I measured the waves to see where they were impacting, to see if they were different between the north and the south. And so you can see the northern site, that low erosion site, is in open circles. And the south side is the closed circles, and they kind of line up with this marsh. And you can see that the northern site, most of the wave energy is focused right at those roots. Whereas the histogram here for the southern site, the high erosion, is very spread out, right? And so if you kind of break this down into percentages, at that low erosion site, a third of the energy is going over the top, a third is hitting the roots, and a third is going below. But here's where it really pops, is that at that high erosion site, 2/3 of the wave energy is undercutting those plants. So here, that biological interaction is driving these changes in erosion. Now, if you were keen eye, you might have noticed something interesting. So I showed you the soil strength with depth, that it was high at the surface. But you'll also see that my north and south sites actually had different soil strengths. You might say, well, maybe just the soil strength is your whole story. Maybe it's not this root thing, but I actually think it ties to the same hypothesis. And so how I'd explain that is that when the winds blow from the south, impacting that northern shore again, the water level's high, and the sediment in the water is able to go on top and accumulate and cause the marsh to grow higher. Whereas when the winds blow from the north, impacting the southern site, there could be a ton of sediment in the water, but it will never get on top of that marsh, and that marsh will not be able to keep growing up. So to test to see if this is true, I went out and measured marsh elevation, and it was true that there's about a 5-centimeter difference in elevation between those two marshes, even though they're super close to each other and have the same plants. So turns out that water level really mattered. Where the waves sit on the marsh edge, the marsh elevation lead to this asymmetry and erosion. So what? I found this out for this one marsh. How does that help our problem that people are losing their homes on a daily basis? And so what I wanted to do is incorporate this into a wide-scale numerical modeling format so we could actually use this to predict what was going to happen and develop plans to mitigate the land loss. And so what I did is I developed a numerical model. So I'm going to walk through the base version of the model first. So the basic idea would be that you take a random wind direction, just like you've seen before. You calculate the associated wave power. You make wave power proportional to erosion. So bigger waves, more erosion, right? Makes sense. And then you use a probabilistic erosion formulation to calculate land loss across the entire basin. I can go more detail later after class if you have questions on this, but it's a little bit more. So what does this look like? So here's a video. So the dark blue here is land, water, and then the yellow cells are things eroding over time. So you can kind of see where there's more open water, there's more erosion, there's bigger waves coming here impacting this edge, right? Make sense? So that's what the model looks like. And it's all great. At first glance, it looks pretty good. So here on the left is reality, and here's what I modeled. And so the yellow is that land loss between 1877 and 2017. And you're probably saying, hey, those look pretty darn similar, right? The yellows look similar. And you're right, at first pass, this basic physics-based model does capture most of what we see, but if you look closely, it does not capture that north-south variability that we actually see. And that north-south variability is on the order of 5 to 10 meters a year sometimes, so this actually does matter. So to incorporate my findings, I changed the model. And so this time I used the random wind, calculate wave power, and I made wave power proportional to erosion, but I made it depend on where the wind was coming from. And when you do this, it's a very simple correction in the model, but now you're able to recreate that north-south asymmetry throughout the basin. And so I designed this model where it's only a one-term change that they can use in like the government official modeling for able to make coastal restoration plans. So this was supposed to be able to easily be picked up and put into other modeling frameworks. rather than just sit in the scientific literature and never be used, right? But what I thought was cool about this model that has really been maybe the neatest part is that there's a lot of larger implications where we can use where the model does well and where it fails to make our predictions and make our sea level rise adaptations. So these are just sections of the model, and so to kind of orient you on the colors, the dark blue is the land, light blue is the water. Yellow now is the land lost between 1877 and 2017 that the model predicted correctly. All right, so that's happy place. Now the bright green color is where the model eroded and shouldn't have, so that place is still land today. And red are areas that the model didn't erode, but have actually eroded in real life. All right. So we actually do a pretty good job, especially if you look in this top figure, you can see there's a lot of yellow, right? And basically what that can indicate to us is in the areas where there's a lot of yellow, a lot of match between the model and reality, wind waves are the dominant process, and we can build wind wave protection structures to reduce our coastal erosion. This is a really low cost effort that can save meters of land very, very quickly, right? So if you're worried about land loss here, if your fishing camp is here, putting wave protection structures here will do a very good job at mitigating this land loss, right? But then another thing you might be like, okay, over here, there's a heck of a lot of red. Yeah. Red normally is bad, but I don't see it that way. What I see here is that these areas are not driven by wind wave land loss. And so we need to think of other strategies in those areas. So we can't apply a one strategy fits all to this area. And so here I would recommend something like thin layer placement, where we actually spray mud using a big hose to cover the entire marshland to try to give it elevation capital so that we can fill in those holes. And so those are two different strategies that were being used pretty haphazardly. Using my model, they've been able to better pick out sites to more optimally use our money to be able to implement these projects. Pretty cool, right? So even where your model doesn't work, it could be really valuable for stakeholders, right? Another interesting thing that I found is I started noticing that the little green areas, the places that still existed in real life, but probably shouldn't still be there, they were weird shapes. And so I went on a Google Earth field trip, started flying around, and I start looking at these really weird shapes. And it turns out that those are all marsh creation projects. And so there are places in Louisiana where they actually build like a box in the ground and they pump in sediment, and like within a year you have a built marsh that you can stand on. It costs a ton of money, a ton of carbon, but politicians love it because you can see the change right away. So this one here, for example, this was a created marsh where they diked that in, built that land. So we can actually see the exact amount of land saved from the restoration. We can calculate a carbon storage capacity, so you can give a dollar value. And this particular one is really good nesting ground for the brown pelicans. So there's actually a lot of focus on that for this particular restoration site. So this kind of modeling framework that's really reduced physics model. So it really only incorporates very simple processes. We're still able to make kind of some ideas of how to implement restoration projects now without having to wait, that are cost effective and efficient for the people who live here. One of my least favorite things to do, so when I go to the stakeholder meetings, all of the science in Coastal Louisiana is really done with the community. And when you'd go to talk to the people down in the parishes way down south, there'd be police presence there to make, because people get really upset and people be like, okay, my house is right here. How many years do I have left? Right, and that's a question I don't really have a good answer for you, but that's one kind of difficulty in working in these type of environments. So my model did really, really well generally across Barataria Bay, but if you started to go north, you started to see a lot more red. So this is kind of a big area within the middle of Barataria Bay where you see a lot of red along the edges of the marsh. You would think that the wind wave model should capture this. And so I drive around and try to figure out, like in my boat, to try to figure out what was going on. I liked being down here, this little channel. You can drive down this little channel and then kind of come up here. And I'd say, well, why on earth are they not matching? And what I started to notice along this gradient is that there are different plants that exist here. So the model that I'd shown you before worked really well in salt marshes, but the area that was doing poorly was a brackish marsh. And there's different plants which lead to different root structures that might affect this relationship. And so you can kind of see the salinity gradient. So this is a GIF showing over time, but basically you have the fresh water in the north brackish in the middle, and saline in the open water. This might seem kind of weird too, because normally like the way, but basically the river water comes in through this way, but by the time it's come in that way, it's salty enough. It's a weird system to work on. So I went out and I wanted to measure, well, do the plants actually do anything different? Is there erosion differences in the middle of the basin that we need to worry about? Because actually there's way more houses and people in this region. I went out and took 50 cores out in the marsh. So basically, here's a great video. We use a sledgehammer and a PVC, you go and slam it into the ground, you dig it out and you section it out. There's me here, my field team. You'll see what I like to show about this video is right off, we start kind of all looking over here a bunch. There was an alligator right there. We actually stopped going to this field site after somebody put that out. We actually go into the water to take some cores and we did not realize how close we were to getting eaten. But we took all of these cores and went to look back and we picked apart the different roots to see how big the roots were, how strong they were, so you can actually do tensile strength tests. And really dug into what's making the sediment stick together and is it different in salt marshes and brackish marshes. And it turns out, oh, it is a heck of a bit different. So here the y-axis is depth, so this is your sediment core, right? So you're in the mud. This is kind of where the plants are up here. And then this is the soil strength and then the soil bulk density, or basically how packed tight is that soil, right? And you can see the saline and brackish are the two different colors. The two places are different. That's the takeaway for you if you don't want to get into soil characteristics. All right. And so actually what it turns out is in the brackish marshes, they have a lot of like thicker roots and not as many fine hairs. And those fine hairs can actually be much better at keeping things together. And as well as kind of the way the network of roots spreads out, makes a more cohesive net in the saline marshes. So if you've gotten anything from how I work, basically I take this idea and I put it in a model framework to see if we could do this better, right? So basically do the same thing where I take the random wind, calculate the wave power, now I make wave power proportional to erosion, where it depends on the wind direction and the salinity of the area. And I calculate the probabilistic erosion. And voila, we are able to do a much better job. And from these calibrations, we can understand large scale patterns in how the system works. So basically there are deeper roots in the saline marshes and shallower roots in the north, which causes kind of more or less asymmetry and changes with the erodibility as well. And so we're able to do a much better job predicting things and understanding which processes are dominant causing land loss. So kind of the takeaway here is that these physical and plant wave interactions are really driving this coastal land loss, whereas all the modeling frameworks that have been used for decades in the area only focused on the physics, only focused on the wind waves, it never thought about the plants at all. And so erosion doubles between the north and south orientation within all of the bays in coastal Louisiana and actually all the bays along the Gulf Coast. So this pattern extended beyond this basin that I started in. And additionally, brackish marshes eroded twice as fast as saline marshes. So we're not just talking small orders of magnitude, we're talking like kind of a doubling that happened. And so now what do I do with this? I was very excited about this. And so how do I get this into policy? It turns out there's kind of a wall you have to deal with. And so what can we do with this information? And so how this is being implemented in Louisiana, and I want to highlight Louisiana as a forerunner in understanding climate adaptation for the entire world. They have something that's known as the Coastal Master Plan, which is a plan to spend $50 billion over the next 50 years on coastal restoration projects that are range from like wave protection structures to building levees to moving people's communities, so where they pick up the houses on stilts and move them somewhere else. So there's a whole suite of activities, and they're the first people to try to do something so huge, but because they are facing this problem now, right? And they update this plan every 5 years. They redo it with scientists, with community engagement, to be able to try to handle this. So to give you an idea of what these projects look like, so here is coastal Louisiana, right? So here's that Mississippi River again, and here is our friend New Orleans. And so all of these markings on the map indicate different coastal restoration plans that they are doing, right? So for example, these pink are structural protection. These are actually building levees around the towns. The parts that I have been engaged in are looking at marsh creation and sediment diversion. So anywhere there's this brown shading, they actually want to divert part of the Mississippi River there to deliver new sediment. I'm gonna go into this a little bit more in a second, but basically to try to feed those marshes that are starving. And so you also have shoreline protection, and they're building out beaches on the barrier islands. So basically, this is a very comprehensive plan that is all based in science to do something right now, rather than waiting for a more other like engineered solution for the globe. So Louisiana has the largest land loss problem in the world. Probably the next two places would be the Netherlands and Bangladesh. And so those three locations are kind of swapping plans to see what works. So this is a big kind of huge experiment, the canary in the coal mine kind of what things could look like globally in the future, as we think about sea level rise. So the main restoration strategies that I want you to think about in the context of my work is looking at sediment diversion, marsh creation, and wave protection structures. And so I'm going to walk through each of those. So sediment diversions I mentioned briefly, we're kind of redirecting part of the Mississippi River into the marshes to allow sediment to go there so that marsh can build vertically and kind of try to keep up with sea level rise. Does that make sense to you? So basically the idea came from a natural accident. So if you remember that land loss map in Louisiana, on kind of the western side, there was a little bit of land growth, right? There was that little bit of green. And that's been basically the hope for kind of all sea level rise adaptation around the world. So that was this Wax Lake outlet and Atchafalaya River. And these were just river systems that were coming out from a small offshoot of the Mississippi known as the Atchafalaya. There was a ton of flooding that was going on in this city here, Morgan City. And so they decided to dredge a channel connecting the two. When they did this, all of a sudden, sediment came out this way and it started building new land. And within 50 years, entire deltas were formed. Okay? There's actually trees standing on these islands now. So within 50 years, there's been enough sediment to create land that is tall enough to sustain trees. Trees don't like salt water, so they need to be elevated up. So this has been massive growth. So this accident created the idea that we could actually intentionally divert part of the Mississippi River, allow sediment to enter places that need sediment, and then you would get land growth. This is our proof of concept. We have no other experiments to understand it, but basically that's what we're doing. So we have picked this site. So all of my field sites were actually right here trying to understand what's going to go on. And we just broke ground on this structure here, which will actually, so this is the Mississippi River, and at times of high flow, they'll divert some water into this structure and go out into the open marsh. Pretty cool. So this is the largest scale project of this type anywhere in the world. And so we'll see how it works. I think a lot of the idea is that it will work, but it will take time. So this has been a politically rife situation because no politician wants to say, well, I'll see land in 20 years, right? But they finally did start construction here. So how my work is fitting into this plan is, remember I said, well, the salt marshes and brackish marshes behave differently. Which one erodes more? Brackish marshes, all right? So these areas have been saline marshes. We're gonna put fresh Mississippi River water into here, causing a switch to brackish marshes. And so we're trying to predict what will happen. And so a lot of it is focusing on trying to get the right species of plants that have the right root structures to be able to make this a more successful endeavor. I'd be happy to talk more about, I'll talk about the sediment diversion forever. It took 10 years of permitting to be able to do this. But there's a lot of people who disagree with it as well, from not the land use perspective, but the dolphins that live in this area are likely to die from the introduction of fresh water. The the oyster industry, they require a certain salinity. They're planning on total loss of their fisheries. So none of these decisions are easy to make, but there's been a kind of a lot of weighing of different costs and benefits. So be happy to talk about more about that, but this is probably the most controversial coastal restoration strategy in the entire world. Happening right here in the United States. Very exciting. So that's probably the largest project that's going to take a lot of money to maintain, but kind of over a longer time scale. Other projects include marsh creation. So I talked a little bit about this, but basically this is what it looks like. They pick an area that they want to create a marsh, make a nice little polygon. And then they take and spray, this is a little pump that's spraying mud in from the Mississippi River. They'll make this little marsh, they'll plant it. I've gone out and planted them before. And then you hope that it settles at the right elevation, you create new land instantly. Okay, it takes a lot of carbon effort, so the balance between the amount of carbon it takes to build the marsh versus how much it's gonna handle sea level rise, this is kind of a mixed bag. And then lastly was wave protection structures. And so you can kind of imagine how my work fits into here probably the best. So the idea being that the places that I identified as mostly wave-driven erosion, we've been building different structures to help prevent erosion and dissipate that energy. So this is known as marsh terracing. So this is the satellite imagery, and you see all these little fun shapes. These basically are ways to break up the waves. And what you can see is they're oriented in a general north-south direction. Because I showed that, because that those waves the wind is going this direction. So basically this is to optimize the amount of wave energy that's dissipated, right? And so these kind of solutions can act now to actively stop. It actually prevents the edge loss almost entirely, immediately. So this is a really rapid, cheap way that we can make action now on helping these coastal communities. Here, another option is to put riprap or oyster reefs in front, and that serves the same purpose. So I've been out there building oyster reefs to try to save some of the communities. So my work here has really shown that kind of understanding that north-south asymmetry is critically important for modeling this. This has been now implemented into the coastal master plan for all of their planning. So this is the kind of stuff you can do now. It just takes a little creativity and crossing boundaries to be able to understand kind of what we can do for people that can't afford to move or wait. The last component of this project is the idea of moving people. And so you have Selena Valderas Guzman, who's coming in 2 weeks, I think, to give your seminar, and she focuses more on the people aspect. But I want to leave you with this, is that the people are closely tied with that water. I showed you all those images. There's not really safe places to move them near the coast, right? And so a lot of these communities that rely on fishing, rely on the bayous, are being suggested to relocate to northern Louisiana, where they would lose their entire way of life. And so there's a lot of discussion, especially from people outside of the state of Louisiana, that, why do we want to pump all this money into saving this area? We could just move people. But it's a lot more complicated than that. And I hope I've highlighted that to you today, is that we can't just drop and run from the cultural perspective, the ecological perspective, but also there's billions of dollars of infrastructure. I don't like to think about those, but that's normally what makes government do something. But for example, here, this is on the border of the Ile de Jean Charles, which is an indigenous community who relies entirely on the water. Their land is about 5% of what it used to be. And they do not want to move. And so there's a lot of effort trying to find ways for them to stay connected to their lands and their culture. And so this is my favorite part of the master plan at the end, is that says that we have all these great resources, but really it's the people and the culture of Louisiana that's really important. And we need to think about that. Here we're proud of our Pacific Northwest culture, right? And there's unique cultures throughout the entire world. And the diversity that we lose from sea level rise is something we should really think about. So I'll leave you on this quote that just talks about how huge marshes are. They're awesome. And I would take any questions.
So the diversion project, did that used to be a place where the Mississippi River connected, but then there was a levee that was built? So the dolphins that live there now were not, I'm curious about the history.
Yeah, so before 1927, there wasn't levees along the Mississippi River, only in certain areas. There was a massive flood, 27 or 29. There was a massive flood that killed thousands of people. And so then the Army Corps built levees along the entire river, the entire length. So previously there was natural levees a little higher next to the rivers. You might see that here. There's actually some built levees, but basically there would be regular natural floods that would break what we call crevasse splays into the edge. And there would be kind of random places that the Mississippi River would connect to the marsh, but they'd be ephemeral. they come and go, they change locations. So we actually went over like hundreds of placements of that mid-Barataria diversion of where would be the optimal place to do this. And so that was one place that was once connected, but it was definitely not the only. Yeah. And there's not many people that live in that region where it will displace people, but it's one of the only Black communities in that region, next to one of a community that only speaks Vietnamese. And so there's some equity concerns about the location. But it was picked with science mostly in mind.
Is there a kind of dual benefit from that diversion of potentially like reducing the dredging needs, or is it too small scale?
It's extremely large scale, but it would reduce the flow in the Mississippi, so it might actually increase dredging needs. But given the potential, what we expect the land extent growth to be, it outweighs the cost of the dredging. In theory.
Does part of the coastal management plan involve like using dredge sediments to rebuild marshes? And what do you think about that?
Yeah, so all of that marsh creation project that there's that tube, that is all beneficial use sediment, and it's basically a requirement of most dredging. So if you look, I don't know what's the stick. So this little pipe here, this basically is a hydraulic tube that will pump sediment from the bottom of the Mississippi River if they can find enough mud assets at the bottom. Normally it's more sandy to be able, so they are required to use that mud, at least 80% of it, for beneficial use. So to build these marshes, to do that thin layer placement where they spray mud on top, that is all dredge sediment. The problem is within the Mississippi River, the bed of the river is mostly sand. The currents are high enough where the bed is sand, the water is muddy, but the bed is sand. So then we've been looking for offshore resources, mud that's offshore, but then we have to do the calculation of if it's worth bringing that material in. And so there's also a lot of balance of what sediment type is ideal. You put sand, it kind of can build mass more and it doesn't consolidate as much. So there's a lot of things that go into that. So the basic idea, if you're interested in geology, is that we look for paleo channels off the Gulf Coast and look for where we'll know sand and mud deposits are based on paleo channels.
Yeah, you said earlier that like the marshes can't keep up with sea level rise. Do you know exactly how much marsh creation would have to be done for like marshes to catch up?
So there's like the marsh creation, the lateral change. So basically they try to put them at a level and they plan for them to exist for 50 years. And that's another kind of aspect of this, is that engineering firms normally plan for a 50-year time frame, where then they expect after 50 years, those marshes will be eroded away. So it's not super forward thinking, but it's enough time to potentially try to get people to move in a more efficient way, or a way that they're happier with. It's buying us a little time. In terms of the vertical, that thin layer placement where you spray on top and give it vertical, that we've tried ranges of like 2 millimeters to like 10 centimeters of material being put on top. But both of those are brand new experiments. We don't really know exactly how well that will keep up.
Is it possible to identify the different plant types at remote sensing, or would you have to go in the field and identify, like, for the model training?
Yeah, so you can identify them via satellite and a lot of that. And then there's also been large scale mapping efforts since 1920 to map all the marsh vegetation in the area. So there's actually really good maps of this, and you can actually see the kind of salinity intruding north and the plant species changing. So very well defined. Marshes are really harsh environments because it's salty. So there's only a few plant species that live there. The number of species increases as you go towards fresher water. So the mapping is actually pretty good to do via satellite. Can't see the roots though.
Yeah, so the wave protection structures, probably there's a good justification. Warren Bilkey's written extensively about how they get secondary unintended consequences. And do you see some of that, or do you anticipate some concerns about that kind of thing, or?
We anticipate a lot of unintended consequences, and there's a lot of different structure types that we've been trying to kind of deal with secondary flows, siltation behind them, and those type of things that we were referring to. Yeah, so part of it, so some of the structures we build. The other way. So some of them are like this, in order, and then there's actually gaps in between to allow for some more, so we don't get filling in of those regions. Some of these along the shore actually were mandated to have holes cut in so the manatees can come in and out through the Endangered Species Act. So we're trying basically along the Gulf Coast, hundreds of different designs to try to see what the pros and cons of each location are. So there's not a one size fits all, like, you know, I don't design, I basically consult on what I think will happen and kind of help with the orientation. And I go out and build them because it's fun. But basically, yeah, so when you have the waves coming here, then you will get filtration back here, and so then eventually you might have to rebuild also. If these aren't high enough, as sea level rise accelerates, you're gonna have to rebuild these. Right, so thinking about that, these ones are actually designed, they're actually marked vegetation on top to design to try to keep pace with sea level rise, so you wouldn't need to have as much maintenance. But that's kind of a shorter version of we're trying a lot of things.
I think locally, so we have some interesting marshes in Grace Harbor, Willapa Bay. I assume it's also Spartina.
It's not, so these marshes here are Spartina alterniflora dominated, which is a saltmarsh species that's native to the East Coast and the Gulf Coast. Here, Spartina alterniflora is an invasive species. And so I actually have a huge project going in Willapa Bay right now. And so they about 15 years ago sprayed and eradicated Spartina alterniflora. So, and there's no Spartina species within Willapa Bay. There's Spartina foliosa down in California, but I'm still learning all my vegetation for the West Coast, but it's all different. The one that is, there's a pickleweed called a salicornia, which is a much smaller stature with much smaller roots. So comparing those smaller roots with the larger larger tidal range here is something that's quite interesting. But here, because of the high gradients that we have and just kind of the lower relatively, like high slopes adjacent to the beaches and marshes, plus there's kind of a lower rate of relative sea level rise, it's just not as pressing, I guess. But the different plant species really do matter, and the West Coast is kind of open territory as to what these plants are doing.
So subsidence is not a big an issue.
We have rapid subsidence from tectonics. So that's a whole separate thing. And I did model some of that in Louisiana because of the heavy weight of the sediment. Sometimes you get growth faults. But here, probably the biggest would be rapid subsidence due to earthquakes, which is much harder to predict of where that's going to happen.
Okay, let's thank Kendall again.